As we saw in the previous series of videos for the project in Ecuador, RETScreen has a so-called virtual energy analyzer that helps us start a project by providing some default values that may be appropriate for our project. So let's see how that works for this village electrification project in Zambia. The costs that will be provided by the virtual energy analyzer are going to be appropriate for North America, and they're going to be provided in Canadian dollars. So the first major difference we're going to see is that our analysis is no longer in kwacha. Here on the location page, I'm going to click on Virtual Energy Analyzer, and I'm going to say that we want to have a power storage off-grid project with photovoltaics, and then I'm going to look through the descriptions here to find the system that most closely models the analysis we want to do. So our base case is grid extension. So I'll look down here and see if I can find grid extension. And there are some options there. Grid extension in the base case and a photovoltaic plus battery system in the proposed case, or grid extension in the base case and a photovoltaic plus battery plus genset system in the proposed case. So that latter option seems a bit better. And here we see that we have a choice between 240 kilowatt hours per day load and 2,400 kilowatt hours per day load. We don't have an option to pick 600 kilowatt hours per day, which is our actual load. So I can either be too big or too small. I'm going to pick 240 kilowatt hours per day here. I will then import this into the existing file. Click OK, and it says the current feasibility analysis will be overwritten. Do you want to continue? Yes, I do. So for this same location, we have RETScreen's analysis. And I will just go looking through that to see how close it is to what we had and how it might be helpful to us. So I'll start by going back to the file page and looking at the settings, and I'll see that the analysis is in Canadian dollars and the higher heating value has been used, so that's going to be different from our analysis. On the facility page, it is, however, configured in the same way that our analysis was configured. On the energy page, we have the cost of diesel fuel here as $1.20 per liter. I think if you do the conversion, it should be closer to $1.60 per liter. The electricity rate of 10 cents per kilowatt hour is roughly equal to the 2 kwacha that was assumed there. On the power system and load characteristics, you'll see that it's grid electricity in the base case with an annual O&M cost here of $250. So that's all right. However, the electricity load is 240 AC kilowatt hours per day, and we would really like to see that at 600. So right away we'd have to adjust that. The peak load is also 15 kilowatts, not 150 kilowatts, so we need to adjust that. Looking down the notes, we see that this is for 1 kilometer of single-phase overhead power line. Well, we need 35 kilometers, so we can adjust the quantity in the cost worksheet. It's also assumed an industrial AGM or gel battery, so a lead-acid battery. We've assumed a lithium-ion battery, so that's pretty different. It's also probably, if I recollect, assumed a DC-coupled proposed case system, not an AC-coupled proposed case system like we have. So there'll only be a single inverter in their system, whereas there were 2 in ours. If we go to the inverter battery, therefore, we see that these numbers are a bit different than what we would expect. 150 kilowatts in our case, and we assumed a different efficiency. The initial costs have been left out, as in our system. They've assumed 1.2 days of autonomy, so that's a little bit more than we assumed. The maximum depth of discharge is appropriate for lead-acid battery, but very conservative for a lithium-ion battery. So a much smaller battery has been assumed here. Why? Because the load is much smaller. The cost is much lower. Why? Because it's a lead-acid battery, not a lithium-ion battery. On the photovoltaic system, here, we see that the slope and azimuth are very close to what we picked, and so the power capacity is much smaller. One reason is because our load is much smaller, but we also see that it's chosen to meet a smaller fraction of the load, only 83% of the load. So going to the peak power system, here we see that it is supplying 17% of the electricity to the load, much more than in our case. So quite a different way to do this. The cost page has the same cost terms as we had for the most part. There's no inverter there. Why? Because it only has one inverter, not the two that we have. Here's the single phase grid extension. For our case, assuming that I updated all the other figures associated with the size of the load, I would put in 35 kilometers here as well. I'll just take that out here. Here at the bottom we have some periodic costs. It's included generator overhaul, which might be necessary given the generator runs so much more frequently and for a much longer portion of the year in this system here, where the PV system is only providing 83% of the load. They've also included battery replacement. After 8 years, the lead acid battery won't last as long, and they've included some inverter replacement, but it's a relatively small amount. On the emissions page, they find something very different there. This is because they're using the genset so much more than we are. And on the finance page, we have quite a different result, which is not surprising. So you could go through and adjust many of these figures to end up with a very similar result to what we have. However, I think in this case, it might be easier to take the approach that we took and start with a blank feasibility study. That doesn't mean the virtual energy analyzer isn't helpful to us. What we might do is, before embarking on doing that analysis with a blank feasibility study, we might look at what's been done for the similar type of system in the virtual energy analyzer to help us remember what costs need to be included as periodic cost, for example, to see how things are configured, and then use that to go forward with our system. But probably easier just to start off with a blank feasibility study after having looked at what the virtual energy analyzer did, at least in my opinion. Use it as you see fit. So that wraps up this entire video series. Thanks very much for your interest in RETScreen's off-grid model.